Okay, let's go ahead and take a look at another example of a modified box plot. So after about 2/3 of the players have been eliminated from a poker tournament, the number of chips possessed by each of the remaining players was noted, and the counts are shown below. A quick comment about poker tournaments: usually everybody starts off with the same amount of chips, and if you run out of chips, you're out of the tournament. So they're saying about 2/3 of the players have reached that point where they've lost their chips to other players and they're gone. And so now we're going to look at the players that are left over and how those remaining chips have been distributed among them. And the first thing they want us to do as part of that process is to find the 5-number summary. So remember, that's the minimum, Q1, the median, Q3, and the maximum. So we're going to go ahead and start out by finding the quartiles first, since that's where most of our work is. Remember, when you're finding quartiles, the first step is to find location. So I would want to figure out the location of Q1 by doing 1/4 times the number of pieces of data plus 1. And it doesn't say how many players there are here, so we're going to have to count them up. These are each rows of 3, so 3, 6, 9, 12, 15, 18, 21, 24, and then another 4 players. So it looks like there's 28 players here. And then we put the plus 1. And we can do that on the calculator. And if we do, we get 1/4 of 29, which will be 7.25. So then, because that's a decimal, to find Q1, we would want to go find the 7th and 8th numbers in the ordered list and average them together. But this list is not in order. So before we can do that, we do have to put the list in order, and the easiest way to do that is to use the calculator. So let's go ahead and bring that in. So we'd want to go ahead and go to the data editor and enter in the data. So I'm going to hit the stat key. I'll slide this up a bit, I suppose. So hit the stat key and then press edit, and then we'd want to enter all the data. So to save a little time, I did that already, but this is just entered by going down the column, so it's in the same row that it would be for you. And now we want to use the calculator to put it in order. So I'm going to press the stat button again, go to the sort option by using the down arrow, and A for ascending is from small to large. And it says sort ascending, and it wants to know what we want to sort. So we want to sort L1, so I'm going to hit the 2nd key and then the 1 key, because L1 is above the 1 key. And it's just going to say done, but when I hit stat and edit again, we'll see now this data has been put in order. So if I scroll down, I can see here which number I'm on. So this is the 7th number highlighted, 5020, and there's the 8th number, 5160. And we said that we needed to average the ones in the 7th spot and the 8th spot, so we need to average 5020 and 5160. And whatever that average is, that would be Q1. So I'll go ahead and exit out of here for the moment. 5020 plus 5160 divided by 2 looks like 5090 would be our first quartile, and I would just check that real quick in my head to see that that makes sense. It should be something in between these two values, so it should definitely be 5,000 something, and halfway between 20 and 160, 90 seems like a reasonable middle there. Alright, so continuing in that fashion, I'd want to figure out what's the location of the median. So I'd go halfway through 28 plus 1. That's half of 29, which would be 14.5. So now I want to average the 14th and 15th values for the median. And just so we can do it all at once, let's look at the third quartile too. We'd want 3/4 times 28 plus 1. And when you do that one, you get 21.75. So for Q3, we're going to need to average the 21st and 22nd values. So we know what values we want to find in between 14th and 15th. And in between 21 and 22. So let's go ahead and bring the calculator back in. Go look at that list again. Keeping an eye here to know what our count is. I have the 15th one highlighted, so the 14th is right before that. So I have 7,700 plus 7,855. That's going to be the median if I average those two. And then for Q3, we want 21 and 22 since our location came in between those. So 13,472 plus 14,620. Average those values. And then let's exit out of here and do those calculations. So notice the parentheses because there's more than one number in the numerator. And I get all these lucky 7s, and then a 0.5. And just always a quick check, make sure that's in the middle of the two numbers you're averaging. It looks like it is. And then again for this, so in the middle somewhere, probably in the low 14,000, so 14,046 seems to fit what I was expecting. And that's most of our work on this problem. Said to find the 5-number summary. We've got only 3 of them, but the other ones are the min and the max. And I guess the calculator is going to make a quick appearance again. But our 5-number summary is just a list, and it starts with the minimum. So if I go into the list, the minimum will be first, 1150. And then Q1, 5090. Median, or Q2, 7777.5. Q3, 1446. And then, even though I didn't give myself room here, also the maximum, if I go to the bottom of that list, that's 29,670. Just a quick comment, this isn't a right or wrong issue necessarily, but on things in the thousands we usually put a comma. Because I have commas for the list too, I think it's usually best to leave those out here just so people don't get confused about where you're switching from one quartile to another versus just a visual separation on the digits for us. Alright, so there's our 5-number summary. Now we want to do a modified box plot to check to see what the spread of these data values looks like. So we're going to start out by doing a scale. So we only have a horizontal axis on a box plot. Let me just go ahead and bring in the straight edge here to do a little bit of a nicer line. And then we'd want to think about how are we going to number that. And one of the tricks that I like to use for scale is to take the max minus the min and divide that by the number of squares that I have, and then round that up to something nice. So let's go ahead and look at what that calculation would be here. So I would take the maximum number, 29,670, subtract the minimum, 1150, and divide that by the number of squares. So you just need to count those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I'm going to take max minus min divided by the number of squares, which is 20, and I get 1426. So what that's really saying is that if I started my numbering on the far left at 1150, made every square worth 1426, then at the far right I'd have 29,670, and I would have spread this data out to the maximum amount. However, if you do that, that's a pretty messy scale, and it's going to be hard to think about how to plot things. So we're going to round that up to something nice. I would say the two choices would be 1500 or 2000. I like the idea of going in 2000s a little better than 1500, so I'm going to go ahead and use 2000s as my scale. And then when you start your numbering, you want to start at something nice that's probably a multiple of your scale. So since I'm going to use 2000s and this is below that, I'll just start at 0. And then 2,000, 4, 6, 8, 10,000. And 2, 4, 6, 8, 20,000. 2, 4, 6, 8, 30,000. And 2, 4, 6, 8, 40,000. Oops. I'm just going to double check that. Something seemed a little off there. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that's actually right here. I'm just going to move that over a tiny bit. I'll do it a different color just to remind us, but that's the far end. Turns out we're not going to get that far over, so that's not going to be such a big deal. Alright, so we already did one of these, so let me just remind you real quick how it goes. The first part of the box plot that I'm going to draw is the left side of the box, which is at Q1. So 5,000 is right in between the 4,000 and 6,000 mark. Basically, we're at the center there, between those two. So I'm going to go ahead and draw a line there. That's the left side of my box. The right side of my box is at 14,046. So here's 10,000, 12, 14. So that's essentially right here. It's a little bigger than 14,000, so I'm making some attempt to be just to the right of that line, but it's really a very small amount bigger when we're on a scale of 2000s. So there's the box part of my box plot. And then I want to add the median line at 7,777.5, so just a little short of the 8,000 mark for that one. And there's my box. Now, if this was not modified box plot, we'd just extend a whisker to 1150 and 29,670 and we'd be done. I just want to remind you that you only get a outlier on a modified box plot if you go a box and a half away or more. And so if I see that the 1150 is about right, let's see, this is actually 2000, so 1150 is maybe right about there. If you have a whisker that's shorter than your box, there's no way there's a modification needed there or an outlier that's going to show up. If you want to calculate the lower fence, you can, but it really is optional when you can see visually that you have a very short whisker. On the other side, when I go to that 29,670, that's about out to here. That's a fairly long whisker if I draw it in, and that means there might be an outlier on the upper side. So to check for that, I need to calculate the upper fence. So first I would do the IQR. So that's Q3 minus Q1, so 14,046 minus 5090. And that's going to give us the length of our box. So let's see how long or wide that box is. 14,046 minus 5090 is 8,956. That's my IQR. And now I'm not worried about a outlier on the left side, so I'm just going to check the upper fence because I think I probably do have an outlier on the right due to how long the whisker would be if I just drew it in. So I'm going to do the right side of the box, which is Q3, 1446, plus 1.5 times the width of the box, and the width of the box, or length of the box, is 8956, and that's going to give my upper fence. So let's see where that would be. 1446 plus 1.5 times 8956 is 27,480. So that's just short of 28,000. This is my 30,000 mark here. So this is 28. So just a little bit past that 28,000 mark right about here would be the upper fence. So if I have any values past that, meaning on the other side of the fence from where the box is, they'd be an outlier. 29,670 is such a value. Just barely, but it is past it. So at the same height I would do the whisker, which is in the middle of the box, I'll put an asterisk for that 29,670. Now that might not be the only one, so I'd want to go back to the list and check. So stat and edit, and there's that 29,000. So the next lower one is 25,000. That's now inside the fence of 27, so that will be our whisker. So 20,000, 22, 24, this would be 26, so 25 is right about in the middle of that 24 and 26, and I'll extend a whisker to that. So there's our modified box plot for the poker chips. Didn't need to modify the left side because it was a short whisker. The right whisker was pretty long. I thought perhaps that might be an outlier, so I calculated the upper fence. It turns out the max is an outlier, so we marked it as an asterisk. Next lower value in the data set was the 25,000 something, so that becomes our whisker. All right, and now let's do some follow-ups with that. Start to think about how these chips are spread out. So what's the most likely shape for the distribution of the chip stacks? Well, remember, a narrow part on a box plot represents kind of taller data because all 4 sections of the box plot have the same amount of data. So if it's crammed into less space on a histogram, those would be taller bars. So because the right side of the box is a little wider than the left side of the box, and because the right whisker, including outlier, is longer than the left whisker, it seems like the data is more spread out on the right-hand side, more stacked up high on the left-hand side. So this seems like it would be a right-skewed distribution. A long whisker represents a tail, and we only have that long whisker on the right, so long tail but only on the right would be a right-skewed distribution. And then what does that tell us down here? So let's look at part D. At the beginning of a poker tournament, all the players start out with an equal amount of chips. So what does this shape tell us about what happens to those chips over time? Well, they're right skewed on the counts, and that means that most of the players have a low amount of chips, but some people have accumulated a lot, but those tend to be extremes. So it's a little bit rare for someone to have a lot, but there are such people, right? But it's not a high percentage, and there's a lot of people on the low end. So lots of players have low chip counts. And a few have extremely high chip counts. So it's somewhat interesting here that since everybody started out with the same, it's kind of interesting to note that we end up, if you think of poker chips as money, with kind of a lot of people on the less money sort of things, or lots of people that are kind of poor or middle class, and then we have a few people that are very rich, maybe even an outlier where somebody is extremely rich. Only here we're just counting kind of the points in this tournament measured through those chips. Alright, now that we've finished up that modified box plot, let's go ahead and take a few notes on that. One is that the whiskers extend to the smallest and largest data values that are inside of the upper and lower fences. So if we just bring that last graph in again, this was an outlier because it was past the fence. The whisker doesn't go to that, the whisker doesn't go to the fence, the whisker goes to the smallest value, that, or in this case the largest value that was still inside the fence, which was the 25,000 something. On the low end we didn't have to worry about that because we didn't have any values past the lower fence. So that's that first note. Now I just kind of talked through the example here. The steps are listed out in the text. I'm not going to list the page number here just because that can change from semester to semester, but it is located in section 3.2. You can see the step-by-step method there. And then it's also worth noting that the calculator does find quartiles, but it finds them using a different method, and so it shouldn't be used. When you're doing quartiles, make sure you use the methods that are in the book. If you ever do look at the quartiles later on the calculator or other technology and they're a little bit different, that just might be because they used a slightly different method. What I've heard is that there are 8 different methods of finding quartiles that all produce slightly different answers for Q1 and Q3 from each other. So I've tried to pick one that is kind of the smoothest and that I think makes the most sense, but not everybody agrees on that at this point, which is the best one. So as you use different technology or even look at different texts, you might see slightly different values of Q1 and Q3 for the same data set. So don't be too alarmed by that as long as they're close to each other. All right, let's go ahead and take a look at one more example. This time the box plot already done for us. So the main event of the 2010 World Series of Poker began with 7,319 players, and the modified box plot below shows the ages of the last 366 remaining players during that year's main event. Just a few comments about this that you don't need to remember for the test or anything, but in a poker tournament, usually the top or the last 10% of the players, everybody buys in for a certain amount of money, and the last 10% win their money back plus some extra. So 10% would be like the last 732 players. So if we're down to 366, we're down to about 5% or so of the players left, which means all these players have made it to the point where they've made a profit on this tournament. So we're kind of looking at a graph of the players who have done the best in this tournament, and they're finishing up in the money. It's not over yet, but all these people have guaranteed that they're going to make some money on this tournament. All right, so we see the graph there. It's for the ages. What do they want us to know? Use the box plot to estimate the 5-number summary. So the 5-number summary is the minimum, Q1, the median, Q3, and the max. And so one of the things that we want to remember is kind of how the box plot was done. If you drop straight down from this lower whisker, that should be the minimum. So we have 20 here, 30 there. It looks like maybe the minimum is a value around 21. And if you think about it, that actually makes some sense for a gambling problem like a poker tournament. Often you have to be 21 years old to enter, so it looks like some of those youngest folks have made it to the end. and then Q1 would be the left side of the box, so we think about where is that, and it's not in the middle, right? So the middle right around here would be 25. That's about equal distance, so maybe those folks are around 23 years old right there. We're just estimating, so as long as you're in the right neighborhood, that's fine. You know, maybe you looked at that and thought it was 24, but as long as we're in that neighborhood, we're reading the graph, you know, and knowing what the parts are, that's what's important. The median would be this line right here. That looks like about the same distance away from 30 that was from 20. So if that's 1 year after 20, I'd guess that's 1 year before 30, so I would take a guess at the median of 29 years old. And then dropping down from the right side of the box would give us Q3. That to me looks about twice as far as this one, so I think that's 2 years before 40, which would make it 38. And then for the max, we just have to be a little bit careful there. There's a tendency to just say, oh, go to the right whisker, but really the max is the furthest outlier, or if there's no outliers, it's the whisker, but if there's outliers, it's the furthest outlier. So here's our furthest outlier. If that's 2 years before, maybe that's 3 years after 70. Again, just an estimate. So maybe you think it's 74, I think it's 73. As long as we're in the same neighborhood, that's okay. So that'd be my estimate of the 5 number summaries. The minimum from the left whisker, Q1 from the left side of the box, the median from the middle line on the box, Q3 from the right line, and the max would be from the whisker if there's no outliers, but since there's outliers, we go to the furthest one out. If there had been outliers on the left, I'd have gone to the furthest one to the left to get my minimum. All right, so we've got those values, and now let's look at the graph and think about shape a little bit. So what shape distribution would you say these ages have, and what does that tell us about the players that make it to the end of this tournament? So remember, the narrower the section of the box, the taller the graph would be if it was a histogram. So when I look at this, I see the narrowest section is the left whisker, a little wider on the first half of the box, wider still for the right-hand side of the box, and then the most spread out section of data is on the far right. So data is the most spread out on the far right, meaning a tail, and it's the most tightly packed together on the far left, meaning a peak. So it seems like the peak would be on the far left, tail going out to the far right. A graph that starts with a peak on the far left and then has a tail down to the right sounds like right exponential. So that's the severest type of right skewed distribution, that right exponential shape. So what does that tell us about the type of players that made it to the end of this tournament? Well, on a right exponential curve, the peak is on the far left, so it seems like it was very common for younger players to make it to the end, and the older players are more spread out, and that kind of means not as likely. So it seems like the most likely players to make it to the end of a tournament end up being the young ones. Just a quick thing that's worth noting, when you start out with the 7,319 players, maybe that's like this too, right? Well, it turns out that it costs $10,000 to enter this particular tournament, so you would think there's not probably a whole lot of 21-year-olds with the $10,000 entry fee, but maybe a retired businessman in his 60s might be able to afford to do that as his lifetime dream or something. So there might even be more of these older players that enter the tournament, but when we get to the ones that are winning money, it seems like most of them are on the younger side of that age scale. So that's unfortunate for me, since I'm an older poker player. It seems like most of the winners are on the younger end. So most of the winning poker players are younger players. Again, maybe a little bit shocking, but the most common thing is for people to be between 21 and 23 years old. That's where we have people the most tightly packed. A fourth of those remaining players are just barely old enough to be able to gamble, somewhere 21, 22, 23 years old. And then finally, wrapping this up, what do the outliers represent in terms of the application and explain? So when you have outliers, one of the things that's always a possibility is that they represent errors. But that's less likely when the outlier is close to the end of the whisker and when there's several outliers close together. have a little bit of a gap here, but it's not a huge gap where I think something must be wrong here. So we have 1, 2, 3, 4, 5 outliers, and I just think they represent unusually old players to be making it to the end of this tournament. So these just represent unusually old players making it to the end of the tournament. And just being a little bit careful there with the phrasing, unusually old. I mean unusual because it's uncommon in the set. It's an outlier. It seems to stand apart from the rest, so it's unusual in that sense. I don't think somebody who's 73 is necessarily unusually old just as an individual, but when you look at this data set, they seem to stand out quite a bit from the bulk of the players that are left. So they're unusually old in the sense that they are much older than the middle 50% of the data, which is the type of measurement we're making with an outlier, saying it's unusually far away from where the middle 50% is. All right, and it would always be possible with an outlier and something we should consider that maybe it's an error. But again, that's more something I would think about if that oldest player was listed as 142. I'd think, wait a minute, I think that must be a mistake, and I would go double check the data value. All right, that's it. That wraps up section 3.2.